Okay, good morning. Today we are going to talk about polymers. We were talking about composites last time, polymer-based composites, and now we concentrate on polymers. First of all, it is important to know that there is a substantial difference between a polymer and a plastic, since the polymer is the main component of plastics, but to get to this plastic behavior, the polymer needs to be added with some other substances. There are some classes of chemicals which need to be added, like the functional additives, which have a number of different properties, including, for example, plasticizers. It is important to remember that plastic behavior can be enhanced by the fact of adding some other chemicals. And then we have some, for example, some substances which have some antibacterial effect, other which might create a foam. Instead of having a solid plastic, you would have a foam. So a plastic which contains plenty of cells or voids, and therefore it might be thick but light, like styrofoam, for example, which is obtained from polystyrene. Then we have some colorants, and we have as well some fillers, which are typically ceramics. Fillers are used in plastics because we have to control the behavior of them. And you may remember that we were talking about rheology, and rheology is the study of how the materials, how the fluids flow, which not all fluids are really liquids. They might be Newtonian fluids, therefore which they fill the container in which they are placed. But in most cases, plastics have got complex behaviors in terms of flow. And this is important because if we want to produce plastics, we need to fill the mold and then to extract the material from the mold after cooling it down, etc. Therefore, we need to be sure of how they flow in terms of velocity, and therefore you apply a shear stress and you make them flow. And also to control the possibility to fill all the parts of the mold, and therefore to produce the piece of the size and geometry we want. We talk a lot about plastics because they are connected with environmental problems. Now we talk a lot about plastics because they appear to be responsible for a number of problems, of environmental problems. Here, what is shown is the table that indicates the possibility of end of life of treating plastics in some way. We would like to avoid to landfill plastic. You see at the right. Landfill plastics means that we can have emissions. Emissions means that something burns and you might have gases or vapors which might contain some toxic substances. This is very general. Leaching means into water. They can degrade. which means that you can have the so-called microplastics. Here we are starting to talk of plastics which are produced from oil, therefore fossil based raw materials. So the so-called petroplastic, the traditional plastic. In the last lectures, we were going to talk also a bit about bioplastics. Now there is a lot of interest about bioplastics. And this has some advantages, but also creates some problems because not everything can be substituted with bioplastics. It's not the so-called panacea bioplastics. They are not going to solve every problem. Anyway, we can have then some release of plastic particles, for example, into sea. We know all too well about the activity which has been done by Greta in the last couple of years about microplastics. This is something we know well, and once they have degraded, there is not, please consider that there is not only biodegradation. Plastics might not be attacked by bacteria, but might degrade, may degrade, for example, for mechanical degradation, or simply speaking, by photo degradation, for example, because they may absorb the sun rays, solar energy, and this might lead in the long run to their whitening and then to their fragmentation. This might happen also from the mechanical point of view, because they might, for example, absorb a little bit of water. In principle, they are hydrophobic, this kind of plastic, petroplastic, but in reality, they tend to, in the long run, they tend to absorb a little bit of water, also because you may see that there are a number of additives which they are not completely hydrophobic. Plastic would be hydrophobic if it is produced uniquely by hydrocarbons, because as you may realize, hydrocarbons don't contain oxygen atoms, and therefore they are not likely to absorb water or to be hydrolyzed in any way. This is not true for in other cases, because with all these additives, you may likely to absorb some water. We have other possibilities. We don't want landfill of plastics, of course. We might consider, for example, we might consider a burning, hopefully not open burning. We would like to have some energy recovery. What is done is energy recovery. The difference between open burning and energy recovery is that we use the energy which is developed in combustion for other purposes. For example, we might use that energy to heat up some water or some air current, air streams, and therefore we to use this energy, for example, to produce electricity, say. So there are a number of options. And a big distinction is done in the case that plastics are used for food, in the food sector or not, because in the food sector we don't accept degradation of plastics into food. That's why in some cases food in plastic packaging needs not to be exposed in the sun, not just because the food would degrade, but also because the plastic degrades. So this would need a lot of discussion, but let's go forward and try to understand better what's the matter with all this. Of course, plastics would also be reinforced. The difference between filling and reinforcement is that reinforcement is supposed to give a higher tensile strength to plastics, like it is the case in composites. As I was saying, glass fibers, carbon fibers, basalt fibers, etc. The last lecture I will do, which will be in a couple of weeks' time, because we have, after this lecture, we have 3 more lectures, will be on natural fibers, because another possibility is that you can add to plastics natural fibers like hemp, like flax, jute, and this is a possibility. This is a possibility which has some advantages because you are more sustainable. The end of life of glass fibers or carbon fibers is not that easy to be treated because they tend not to be degraded in any way, and so it's difficult to separate them from the resin, from the plastic. Okay, let's go forward and try to make more sense about how we classify plastics. You have seen, I'm sure, these numbers in most food containers, and not just food containers, also packaging. Any kind of packaging which are made in plastics have got these numbers. This summarizes what these numbers are for. And these numbers are put especially because we're supposed to recycle plastics. Recycled plastic means, recycling plastics means that we melt or we soften plastics. Melt, why I don't say melting? Because in reality, you can say melting from a physical point of view, you can say melting if you have crystals. In most cases, this is important to know that plastics are not polymers, and therefore plastics are not, in most cases, crystalline. You may have some quasi-crystalline polymers, but, and I'm showing something of that as well, but this is not usually the case. In most cases, polymers are amorphous. Therefore, they soften rather than melt. As I have already said, but this is important, we don't have a precise temperature for melting, but we have an interval in which the solid plastics softens, therefore becomes somehow fluid. So it might be somehow processed. It might be somehow recycled at end of life. At end of life, you make all these chips. You make these plastic chips. You grind your plastics, and then you soften it and try to make material. And other plastics basically, but with a lot of difficulty because you consume energy. You produce something which is thermodynamically inferior, of lower quality, and a number of other problems. You don't consume just energy, you might consume water. In recycling paper, for example, you consume a lot of water. But we cannot talk about everything, but just have some clues of what's happening to material. So these numbers are put because some of these plastics are easier to be recycled, others are less easy to be recycled. We recycle very well number 1, which is the one used in bottles, which is polyethylene terephthalate. We recycle it quite well, although the reduction in quality is always there, you lose the transparency, first of all. Then the structure cannot be recomposed as such. What I mean very, very simply is that from a bottle, you don't make again a bottle. You make some fluffy material from which you can take a part of it and add to a new bottle, say, add from to new plastics to make a bottle. The advantage with number one and also with number two and number four is that, and number five as well, is that they basically come from hydrocarbons. The polyethylene, I don't know why these are, I will delete it anyway. The number one and number two, number four and number five, they are basically based on on hydrocarbons. So we have a polyethylene terephthalate, a polyethylene high and low density, which doesn't mean a big difference of density. The density is around 9.9, but high density it's slightly higher, and you can make more resistant stuff. Like you can make, for example, heavier and thicker bags. Number two. Number five, we know it all too well. It's polypropylene, which in Italy is called the moplan, and also used in a large number of packaging items, but it goes out from the packaging items. For example, you use it in car bumpers as the matrix for glass. Polypropylene is used a lot as the matrix with glass fiber. Most materials in car industry, most light but resistant materials in car industry are made of polypropylene matrix and glass fiber. They use also carbon fibers in car industry, but not in the usual cars we use. In racing cars, yes, they use carbon fibers, but they are much more expensive and rigid. But they are able anyway to absorb a lot of energy, which is useful in case of accident. We have trouble with number three, which is the polyvinyl chloride, which is the oldest one in historical terms, because it was used already in the 30s, and so before the war, and it contains, as the name says, chlorine, which means that once you reprocess it, you are likely to have environment which is going to be heavily acid or basic, and so it's difficult to control the pH, and it's difficult in many cases to reprocess without having chlorine emissions, etc. You can make it, but the question is also that of use of PVC it's very spread. What I mean by that, I mean that it's used a lot, but in a large number of different products which have nothing to do the one with another. For example, it's used from credit cards to the shower curtains, which is very when you use a plastics from in industries which have no connection between them. The problem is that at the end of life, who is going to take charge of that? And it's also used in laminates, which are quite complex ones. For example, recycling credit cards, which is becoming a quite largely used product. It's a problem because it is a laminate. It is a laminate that includes some metals, that includes a number of different plastics and includes adhesives, because everything is put together by pressure with adhesives. Well, therefore, it might number 3 is already quite a problem. Number 6, it's a problem. Polystyrene, it's a problem, especially if you have styrofoam, because with styrofoam, the operation that was made is to produce a foam with a foaming agent. The most common foaming agent, still the best one, it's oxygenated water. So you add oxygenated water and it swells. And when it swells, what you obtain large thicknesses and light weight. Therefore, the volume it's large and the value it's very low. So in the end, we use it a lot, but we don't make much money to recycle it, because when you recycle it, you chop it and you press it again to try to come back to polystyrene. What happens is that you can get a large volume. Let's consider that you get on a truck and you want to get a load of styrofoam, and in the end you might fill a whole truck, but in the end you end up with a few kilos of plastics, so little value. It's unlikely that even you are able to pay the person driving the truck. I give you this simple example to understand what's the problem. Well, there are a number of methods to recycle polystyrene in the foam version, so styrofoam, but in practical terms, you don't make much money. So in the end, it's not recycled. 99% of it is still not recycled. It's landfilled, which we wouldn't do, because it contains, since it is styrene, it contains some benzenic components and so some aromatic component, which in the end might less problems we have with polystyrene non-foamed version, solid version. The solid version has less problems and it's almost to the same level of polypropylene for recyclability. It's also used in a few products and might be likely to be recycled. It depends always on the field in which you use plastic, if you are able to recycle it or not. Because, for example, there are some fields in which recycling is not allowed, like for medicines. For example, you use a lot of polystyrene in medicine bottles, for example. Medicine bottles are unlikely to be recycled because they end up in hospital or in specific landfilling sites, and at the end of life, it's tricky to dispose of them by recycling, because they need to be separated from all the rest, for example, for medicine blisters, drug blisters, etc., and syringes, so on. So in some cases, it's not easy to recycle that. Number seven is all the rest, all which is not mentioned in number 1 to 6. It goes, in fact, it's marked as O or other. Here there are some plastics which cannot be thermally recycled because, put it simply, they don't soften. These are the plastics which we call as thermosetting. Plastics that don't soften are called thermosetting. Then there are a number of plastics which are used, very high profile plastics, which are used in little amounts, in reality, like polycarbonate, even polymethyl methacrylate. I mentioned the plastic by the name of the main actors of the polymer, but of course, please be aware of the fact that plastic and polymer are not synonyms. And other plastics, so there are the thermosets like epoxy, like the so-called resins, and also some thermoplastics which are used limited, like polymethyl methacrylate and polycarbonate, etc. Well, the polymethyl methacrylate, it's the so-called plexiglass in Italy, and or PEX in the UK, and this is going to be more used if we have to be confident in what the newspaper and media says about the end of the virus, etc. And therefore, the problem of recycling will be considered. Anyway, polymethyl methacrylate is used for long duration items, so the problem of recyclability might be limited because we will have a little amount of waste over a long time. So the impact would be more limited. Nevertheless, the problem needs to be posed. And I was talking about recycling. Recycling it is in this strategy, is inserted in this strategy, and which represents what we are supposed to do with waste. The first option would be not producing waste at all. We can spend days in saying how this is done. But first of all, you could reduce the amount of waste by redesigning items using lower amount of materials, make the object lighter. Multinational companies spend a lot of time in order to reduce the weight of their object. For example, let's consider IKEA. IKEA spends a lot of time in trying to make for example, a chair or any kind, a wardrobe or any kind of furniture, or bed frame, in order to make them lighter, so less material, but with the same strength also about. So, apart from redesigning, there is also the question of possibly repairing, reconditioning. We produce less waste if, taking a mobile phone, we recondition it instead of disposing of it by landfilling, I hope not, or in other ways. So there are a number of considerations which will need to be done. Please consider that one important thing is that, as always, it's more important the understanding the method of reasoning in material science rather than remembering the right numbers and whatever, because they might change also. It's important to remember that reuse is not recycled. By recycling, you change the geometry, you produce something else. By reusing, you basically don't change the shape, geometry of the object. You might use the object in another way. Coming back to the example of IKEA, IKEA has done a lot of research to give a second option, second reading, as the designers put it, to an object. So this was children share, now your children have grown up, you can use it as a container box to put books, say. Instead, you reverse it and you use it in another way. This implies the fact that this doesn't become waste once your children have grown up. Of course, there are other options. You may donate it to a charity or to a friend which has younger children. That's an option. Or you can reverse it and give a second reading, a second use. So you prevent the formation of waste. The best option is to produce less waste. We are overwhelmed by waste. If you don't succeed with that, there is recycling. So you grind, you chop everything mechanically, and this can be done with any material. Then you soften or you melt it. In case of metals, you melt it. And so on, and then you produce another object, which on thermodynamical grounds, once you spend energy, you have a transformation, spend energy and water, etc., then you have a second object of lower quality and of lower strength, etc. Because the two things are connected. It's likely that the user will be of lower quality, etc. Other recovery means that you can usually recover the energy. So you might have other ways of recovering. You can burn and recover energy. With that energy, you can heat water, as I was saying before, and produce some other kind of energy, transform into some other kind of energy. Disposal needs to be avoided unless you have inert materials. When I say inert materials, it's like rock, stones, etc., which have no action on the soil in which they are landfilled. So basically, they stay there for the eternity without doing anything. This might happen with some kind of sand, some kind of rock, etc. Not with all ceramics. There are ceramics which have some action. For example, if you put lime absorbs water and change of the shape, geometry, may produce further effects. So the inert is limited as a category. Even if you have glass powder, if you powder glass from glass fibers, for example, they might have some action in the sense that they might go around and may even taken away from stream and so on. So in the end, you might have problems because they may leach into water. So it's better to avoid the disposal unless you are not sure that the material is clean. Instead, we are still doing a lot of disposal into landfilling number of substances and of toxic or non-inert materials anyway. Okay, so plastics. Let's come to plastics. To going deeper into that matter, there are not just petroplastics. Here we see four categories, and these four categories are one we know. That's the one we know, which is bottom left. So basically, plastics obtained from polymers developed from petrochemical raw materials, so hydrocarbons, whatever, polyethylene, polypropylene, polyethylene terephthalate, polystyrene, and they are not biodegradable, so they are not attacked by bacteria. Having said that, this is the general situation. Having said that, there are petroplastics which can be attacked by specific bacteria. So we can design some bacteria in order to attack some specific petrochemical. This is well, I will go into more details about this, but for example, there is a worm which attacks styrofoam. The Tenebrio molitor, it attacks styrofoam. But what I'm saying, so I'm not saying this quadrant has no value. I'm saying in general terms, so let's put into a general landfilling site. These materials bottom left, they are non-biodegradable because there might be any kind of bacteria. In general, they are non-biodegradable. This is very rough. This diagram, it's useful, but as many models in engineering, it's very rough. What I'm saying by rough, it says that for example, that these materials are non-biodegradable. Then there is a big question. Between non-biodegradable and biodegradable, there is a big question, which is the velocity. Biodegradability, to be useful, need to be quite fast. Otherwise, it's not useful for any purpose. I mean, if something degrades, but in thousands of years to decompose, well, this is not of any purpose in reality. But and therefore we can say non-biodegradable, so very slow, or biodegradable, so reasonably fast. So please consider that this is a rough simplification, which is useful, because most laws in engineering are useful because they are very simple. Then top left, we have there is a possibility to produce the same plastics, because we are very happy with polyethylene, polypropylene, polystyrene, polyethylene terephthalate, etc. We are very happy with them because they are light, they cost little, they can be used for a number of purposes. In 50, 60 years, they have invaded every place. And they are moldable. Moldable means that they can be produced in a very large amount of pieces with molds which can be used millions of times. This is a difference from metals. You may remember that there are molds also in metals, to produce cast iron pieces, so steel pieces, cast iron pieces, copper pieces, etc. But the disadvantage is that these molds can be used only one or a few times. Here, the molds can be used millions of times, so I can produce millions of PET bottle with the same mold, and the mold will be not damaged. So I can carry on using it. Consequence, the cost of the mold is much higher than the cost of the single piece. Other consequence, when I want to change the geometry of, say, a bottle, I have to think a lot about it, because the mold is the main cost I will incur. This is important to know. That's the mold, it's the factor which is kept constant. I may change many other any other aspect. For example, I can change the mix. It's easier to change the mix between the polymer and the additives, provided they fill the molds, to fill better the mold. So I need to adapt to the needs of the mold's need. I'm not treating the mold as a person, but it is the object I have most to care about in plastic industry practice. That's how it. So we coming back to my current, I am happy with these plastics. I would like to use these plastics, but the problem is that I don't have um, I don't have initially we didn't have any any environmental concern. I was using, for example, in research, polypropylene glass fiber composite for car bumpers 20 years ago, and didn't care much about the end of life. Now there is this concern about the end of life, about the possibility to recycle and the possibility to reduce the environmental impact. Because what do I mean? If I produce plastics from oil, I contribute to resource depletion. So I have to extract and distillate oil in order to get hydrocarbons to make the so-called cracking, and I have to obtain hydrocarbons to produce plastics. In the end, oil is reduced more and more. So why not using other materials, for example, materials which are obtained from agriculture, to produce some plastics? The same plastic, I would like you to obtain the same plastics, so the polyethylene, polypropylene, polyethylene terephthalate, because I'm happy with them. And so I call them biopolyethylene, biopolypropylene, and bio-based. Bio-based, exactly. This is the whole term. Bio-based, because, for example, a simple example, I can produce polyethylene using ethanol. And ethanol is obtained by the distillation of a number of sugars or polysaccharides obtained from plants. For example, from sugarcane, I can obtain ethanol. I can produce liqueur from that, or I can, why not, use that ethanol to produce plastic. That's good. That's possible. That's bio-based. But that's not biodegradable because it's the usual polyethylene, polypropylene, etc., which is not biodegradable. Moving to the right, I can have some biodegradable plastics, so biodegradable, which I am not able to recycle, but they will degrade in the environment. Once chopped, once ground to as powders, they can degrade into the environment. And I can produce them from the agricultural, so polysaccharides, and mainly from polysaccharides, proteins, bacteria, PHA, polyhydroxyalkanoate is produced from bacteria. Polylactic acid is produced from glucose obtained from starch. I can obtain these from polysaccharides. They are biodegradable and they are obtained from renewable raw materials. There is also a fourth category, which is obtained from oil, but biodegradable materials. I can some biodegradable materials also from oil. They are biodegradable, but they are obtained from oil. So I consume some oil to produce this plastic, but they are biodegradable. Like the polycaprolactone is the more popular one. It's used a lot starting to be used a lot in DIY works and so on because it softens at 60 degrees. polybutylene aditate terephthalate, PB18, for example. And they are biodegradable but obtained from oil. So this is what the quadrant says. As always, there are midways. So there is something which is biodegradable but slow, and there is something which is partly obtained from renewable raw materials and part obtained from petrochemical materials. Because one of the characteristics in the plastic production is the creation of blends. In metals, we call them alloys. Here we call them blends. We blend the different types of plastics. We might have other chemically more suitable options like the creation of copolymers with some interaction, or we might just blend, put them together with no real interaction. I take 50% of that, 50% of that. For example, I can take 50%, this is quite popular, 50% of polyethylene and 50% polylactic acid, PLA. And I get something which is sort of biodegradable but low. It might be, I hope it biodegrades once I finish it. This is a big field. I can spend a long time. Let's try to proceed and to concentrate on that. You know that there are thermoplastics which soften when heated. They are branched they are branched but flexible. They might be branched, so you don't have to think that a polymer is a chain of molecules, which doesn't mean that you have a linear polymer. You might have a linear polymer, or you might have branched polymers which are able to move a little bit. The structure can move a little bit, and therefore you can suppose that you are able to process them because they soften. As always, the concept is always a little bit, these are extreme concepts. The thermoplastic softens, the thermosetting burns, doesn't soften with temperature. Also, thermosetting, as I was saying, thermosetting I use it because they are not recyclable in a thermal way. They are mechanically recyclable, yes. Can chop them and put them into another material. There is a number of questions. So thermosetting, of course, they don't soften because they have a structure, they have a reticular structure, so basically a cross-linked structure, which tends not to deform with temperature, and therefore it doesn't break the linkage and it doesn't soften in the right interval. Here I'm showing an example of one of the first thermosetting. You know, in nature we have thermoplastic and thermosetting polymers. The wood can be considered like a thermosetting structure. Other structures are can be considered like starch, cellulose. Cellulose can be if it is treated with acids, it might be cross-linked, but might be also thermoplastic characteristics. In engineering, one of the first plastics which were developed before the onset of the real thermoplastics. So there was a period in which some plastics were developed, which we now regard as proto-plastics, so plastics before the true plastic. The first true plastic, to say so, was vinyl, so polyvinyl chloride PVC, which was developed in the 30s, and where also some studies on polyethylene started. And vinyl, before vinyl, there were some other kind of plastics like protoplastic, like bakelite, which has still some uses. And it was a phenol-based plastic. So the first plastic were based on phenol, and with the addition of formaldehyde, there were some resins which have had a large success. With the addition of formaldehyde, which was the formaldehyde was basically the first preservative, first universal preservative substance which was able to preserve materials from degradation. Even it was used in embalming, really, for human bodies. It was therefore it was used also to cross link. Plastics to these protoplastics. So we have a lot of phenolic resin products, which this is the possibility of recycling. This is what I'm saying here is that also phenolic resin products, which are regarded as non-biodegradable because they are thermosetting, might be, in some cases, the worst bit is the collection of phenol resin wastes, because they are used in construction, for example, still a lot used into furniture, but it's quite difficult to collect them in large amounts and to have this kind of treatment and to extract again phenol, carry on the project again, and amorphous carbon, which you might use anywhere, and it's also inert, so you might also include into cement or asphalt. Bioplastics, I don't want to talk about bioplastics today because as you can see, the subjects are already quite articulated, more than complicated, I would say. Bioplastics, which are developed at the moment, are obtained from mainly from polysaccharides, from derivatives of sugars, or obtained, there are also bioplastics which are obtained from proteins, but mainly from polysaccharides, I would say. We are going to talk of this in the last few lectures, but another important thing is that you can make, since we are not going to make thermosetting plastics disappear because it's useful to have a plastic which can be treated, which can be produced at room temperature just by adding a hardener. You can do the same operation also, which we have done with bio-based plastics. So bio-based plastic, you can obtain a plastic from ethanol, a traditional plastics from ethanol, for example, and you can obtain also a traditional thermosetting with using some vegetable oils, for example, rapeseed, castor oil, and you can produce some thermosetting from oil. Instead of using, for example, phenol or epoxy, you can produce also some bio-epoxy with kind of, or some thermosetting polyurethanes, also using this kind of. Having said that, let's go into more details about polymers. So here we can see that the situation is not as as simple as you may imagine, because of course thermoplastic, thermosetting, biodegradable thermoplastic, and biodegradable thermosetting, and this is quite really. Olefins, we have polyethylene and a little bit also polypropylene, which is less used. Some plastics have had a large success, some thermoplastic in which has, for example, a resistance to the limitation of plastics, usually the resistance to torsion, because they can even melt to torsion only by the effect of friction given by torsion. A plastic which is resistant to torsion is nylon, polyamide. And well, there are different types of polyamides, but anyway, they are called in general terms as nylon. And you can make even screws or bolts in nylon, which gives you the idea of their resistance to the torsion. You can make wires, ropes. And this is a useful explanation of how things are, more than plastics which are used. And you can see that there are a number of situations which might be in between, because you can have a thermo, for example, in polyurethane, which is diffused a lot. You can have thermoplastic polyurethane, and you can have thermosetting polyurethane. Polyurethane is difficult to recycle anyway, because, for example, foamed thermoplastic polyurethane has the same problem. The material which in Italy we call gomma piuma, it's a thermoplastic polyurethane, foamed thermoplastic polyurethane. And you have the same problem, even worse, that you have with styrofoam, is that when you compress it, you chop it and you compress it, in the end, what you end up with, it's with something which is of less value, not much useful. Polycarbonate, it's a thermosetting, it's but there is also thermoplastic polycarbonate. Polycarbonate is the replacement for, but more expensive, for polymethyl methacrylate. You can make plates, you can make sheets of vitreous aspect, so glassy aspect. So basically they are glassy polymers. One difference which we need to be aware of is that also there are, apart from thermoplastic and thermosetting, there are glassy polymers and rubbery polymers, which have different properties. Glassy, they elongate. In very general terms, glassy, they elongate less. Rubbery, they elongate more, but with glassy polymers, you can be able to make sheets. With rubbery polymers, you can make films, but sheets of vitreous aspect are out of your possibilities. Then you have rubber, natural rubber, which is a thermosetting, although it's less cross-linked than the normal thermosetting, like the epoxy. Then there is the Teflon, the polytetrafluoroethylene, so-called Teflon, and the Teflon has a linear chain, but it doesn't reach much energy, even with the application of the temperature quite high temperature for the case of quite high. When I say quite high for polymers, I mean 300 degrees. Don't think more than that. but it doesn't reach enough energy to allow the chain to disassemble and in practice to solve. So in practical terms, can be used. And then there is ABS. ABS is very interesting. It's used a lot. Design in furniture, in a lot of electrical appliances as well. And it's made of three polymers: acrylonitrile, butadiene, and styrene. Butadiene is more rubber, whilst the other two are more plastics with different characteristics. I will show it in a bit. Well, this is ABS. And ABS is a good example of how you proceed. And it's also, and they have enough amount of ABS that you're able to recycle it, because it's used in a large amount of in large amounts, also because it is also because it's very performant, and it has a number of different possibilities. Acrylonitrile gives you high aging and it resists to heat, whilst green is more glassy and therefore but it molds better, because butadiene is a right kind of rubber, so it's able to go to lower temperature even when you freeze. ABS works well even when frozen, when the weather outside is below 0 degrees, which happens to a number of ABS, so, when I use it in the exterior, because there are some, because they are sensitive, for example, to salt water, etc. ABS is very good to use inside. For example, phenol resins, they are not always very good to be used in low temperatures. And butadiene gives you an impact, a considerable impact strength. When I say impact, I'm going to talk a little bit about impact. I also in last lecture. Impact, you can have heard about sharp impact and iso impact, but there is also falling weight impact. So basically, there is a ball that impacts on your plate, and you see when this ball is impacted, penetrates. This is interesting for some industries like ABS is used. This is another diagram which gives you an idea of the thermal classification. There are some plastics which can be used. In fact, polystyrene, you wouldn't use a polystyrene high temperature applications. As a matter of fact, well, it's stupid to say, but you wouldn't put your polystyrene medicine bottle into an oven. This is stupid to do, but even you haven't seen any container, having oven container made into polystyrene. In fact, in some cases, there are some precise temperature limitations. This is the classification. You can see that there are some plastic which have a very high. I don't go into details about that. You can look at all the acronyms, what they mean, but some are easily recognizable, like polycarbonate, like Teflon, poly, tetrafluoroethylene, and whatever. And this is an important fact. the fact that you have these different range of temperature. Also, you remember how steel was behaving into tension. A semi-crystalline polymer, which is the most common case, so you have a polymer which has some crystalline part, which is usually contained into arranged in this way, in this kind of spherulite. You have you stretch it, because basically you start pulling it, and in the end you have some yielding, so you reach the elastic limit, and then the spherulite starts opening, and you get to a fibrillous structure. Once it has stretched for the, we're talking about thermoplastics and rubbery thermoplastics, and they stretch, and in the end they start to strain hardening. You have this kind of strain hardening, which you notice that also in foams, in compression of foams. Here it is in tension, and you have at the end you have a fracture, of course, failure, but you can have a stretch up to 200, 300%, depending on the polymer. The interesting thing is that here you can see that it's not a straight line at the beginning up to yielding. It's not a straight line, it is a kind of sort of a straight line, but with some curvature. Which means that one very simple thing, that polymers, semi-crystalline polymers, can never be considered completely elastic. They have always some plasticity, some viscous effect. So the time, as always, they have always some creep. I hope we can discuss a little bit more about creep in polymers, but we have creep at room temperature, and we have creep for whatever, even small deformation. In practical terms, we take into account that by considering a elastic modulus, which is made of a modulus which is made by an elastic part and in damping a part. So we have a storage modulus, which is the elastic bit, and we have a loss modulus, which is damping, which is the viscous with the plastic, viscoplastic bit. In practical terms, we express that by a complex number. You may remember that from maths that the root of -1 was considered I. In some other language they say J, but the question is that you are introduced to complex number. So you have a real part and an imaginary part. And so complex numbers are useful in the case of material science to represent the effect of damping or viscoplastic effect, so the effect of time on even the elastic, quasi-elastic part of the they all depend on time. We will go into more details, but both E1 and E2 depend on time of load application. Both the storage modulus and the loss modulus depend on time of load application. And delta is increased with deformation, with time of application of the load and the deformation. And it has some influence also with temperature. So delta, if you remember the study of angles and the study of sine and cosine and tangent, of course. If you remember that, you may remember also that if you want to get the ratio between the two capitals of this triangle, so between E2 and E1, you are to measure the tangent of that delta angle. And in fact, we define that ratio as tangent delta. The tangent delta grows as the delta grows with deformation, since it is an angle between 0 and 90 degrees, of course. It increases with deformation, therefore also tangent delta increases with deformation as well. So the more deformation you have, the more time you have applied your load, the less elastic becomes your material. This is quite obvious. Let's see which kind of behavior we can get. Of course, this concerns instead glassy and rubbery behavior. We have a temperature at which you pass from a glassy behavior to a rubbery behavior. This is called the TG, the temperature of glass transition, the glass transition temperature. The TG, as always in polymer, it's an interval temperature. You have the first transition, which means that it is the TG, and at which the Young's modulus, so the E, which is composed by E1 plus I E2, you have this Young's modulus that drops over a certain temperature interval, and the material becomes from glassy to rubbery. If the Young's modulus drops, that means that the material elongates more. Rubber elongates more than glass, obviously. Then you have another transition, and you get to a fluid. And in this area in which you have a fluid, probably a non-Newtonian fluid, you are able to process the material. Then you have a thermal stability limit, which means that at a certain point you are not able to process the material because it becomes fuzzy. There is a thermal stability limit. This is indicated as it was the same thermal stability limit, but you might imagine it changes for any polymer. So you have a linear, which goes linear amorphous polymer, which goes between a glassy and rubber state, and then it becomes fluid. You have semi-crystalline. Well, semi-crystalline means that they don't lose much in becoming rubbery. It's also, in some cases, it's also difficult to see the TG. In other cases, you can see the highly cross-linked polymers. Basically, they are thermosetting, and if they are highly cross-linked, they are thermosetting, and in the end, they don't show any glass to rubber transition, which is typical of thermoplastic. In the end, though, they end in burning. They don't lose much into terms of Young's modulus, but they burn. In the case of the vulcanized rubber, I may have shown last time. Vulcanized rubber means that you have some bridges made in sulfur by sulfur atoms between the different chains. This is called vulcanization, and this allowed the production of tires, of car tires, etc., by a patent which was by Goodyear in the 19th century. And in the end, what happens with vulcanized rubber is that you have even an increase on a kind of hardening when it becomes rubbery. So it becomes rubbery at a certain point. At low temperature, it becomes rubbery, because we will discuss more about TG next time, because it's important to know where is your TG. Because it's important that your TG doesn't get into the way of the service temperature of your material, because if TG gets into the way, you are not able to use your material anymore. In other words, if I have a TG at minus 10 degrees, which is the case, for example, for some polypropylenes, if I have my TG at 10 degrees, that means that if I use a polypropylene chair in the garden in a cold country, temperature gets into 10, the polypropylene chair with my polypropylene being rubbery will become glassy at minus 10 degrees, and therefore I can sit down once the chair has been done in the cold at night, and it will break because it becomes more brittle and undergoes some transformation to glass. So it might not be able to withstand the so-called freeze cycles. But we are going to discuss more this later. There are some polymers which are amazing, like polyether ketone, polyether ketone, the PEK, which costs a lot, but it is a conductive, a sort of conductive polymer, because we assumed that polymers are insulating thermally and electrically, but in reality there are some polymers which are crystalline, and in fact you can see from the curves they are basically crystalline. You don't see that big elongation. You can see that the strain, it's very limited. They are crystalline and they are glassy as well, and the polyether ketone, so at room temperature, I'm saying, and basically you can use them by adding some carbon fibers. This has been done in the aerospace industry. They do composites with polyether ketone and carbon fibers. Very expensive, but very performant. They can go at a temperature as high as 300 degrees with no damage, and they are conductive. And now they have done some number of experiments into making some membranes, conductive electric. You adding some carbon fibers and also some graphene nanoplatelets to be able to make also these membranes very conductive with very small dynamics, so conductive layers with very small. Because what is usually done with polymers to make them conductive is to introduce to treat them or to introduce them with some conductive materials, like it could be the case with metals and so on. Another possibility is this one, to take already a polymer which is already conductive, equally conductive at the same level, carbon fibers or graphene. This is a very recent research, and this is the field in which people works right now. So there is also an advanced research on polymers. They are not just commodity. Summarizes what we are saying. I'm not carrying on very long from now. So there is always a mechanical recycling. There is a thermal recycling if you are at the thermoplastics, and in some cases you can push that, and you can crack your base plastic waste. Basically, you might have polyethylene, polypropylene. You might consider that you can absorb lime. You can absorb lime or whatever ceramic. There is always a ceramic into a polymer. You absorb it, and you are going to use in some other applications, and you get in the end hydrocarbons. You can get to the polymers. You depolymerize, and you get to the hydrocarbon, and you can carry on using that hydrocarbon to produce other plastics, to make other chemicals, etc. For example, if it is ethylene, you can consider producing ethanol. Um, this gives you an idea of what happens with the production of polymers. In practical terms, we are going to talk of this next time, but I give you just some indications. There are two processes for producing plastics. You have an injection molding and extrusion. The temperature of the different section of the screw and the no-end screw, which you use for this process of the extruder is used to produce some elongated piece of constant thickness. And basically, you have these different sections with different temperatures because the flow changes with temperature, and you have to consider that. And it is very sensitive to the difference of temperature, and it is very sensitive also to cooling down. When you cool down, when you put in the mold, you need to not by an abrupt amount of cooling down. In some cases, in extrusion, for example, which is this is the case for polyethylene, so the melting point need to go over that melting point at some points, and you have to control the flow, and you need to consider also the screw speed, because you have basically that rotates and allow you insert here some pellets and granules of plastics in the sense that I have polymers and all the additives, and I make the granules, and they gradually melt at different temperature, and I control the process of moving around. I may have a number of problems. I may have a number of problems before I optimize that process. I may have blisters, got some air entered. Something can be burned because I exaggerated with temperature in some sections. I might have exaggerated instead with the flow velocity, so I might have some burn. There is this part which I didn't really want. I didn't want. And therefore that means that it was going too fast, and I had produced the end. I produced a piece of geometry which was imperfect because of the flow of the plastics, and I might have flaky surface for mixing, because there is also a question that once I melt, I soften the granules, mixing should go further during the whole process in order that I composition that I get the same composition from which I start at the end, which is not always the case. I need to take, of course, some measurements about that. So in some cases, I need to I measure, for example, with the viscosimeter or rheometer. I have this plate cone, which is a typical situation. I have this cone, and I can measure the viscosity by the basically by the momentum of the torque, which is needed, the pair of forces which create a torque with a moment, which I need to apply. This is done with the so-called meatus of the fluid. So the fluid which passes through here, which with a very small angle, and basically I have the plate is stationary at the beginning, then the fluid starts passing through, and I have to apply a force, a torsion force with the momentum decomposed in two forces, so that I can apply a momentum in steady. And I use this very small angle because I want that sin theta is equal to rather equal to theta. And therefore, I can measure the viscosity in this way. You can recognize the volume of and so this is the velocity of application of shear stress. Remember that when I want to make something flow, I apply a shear stress, and from that I measure the viscosity. The higher the shear stress I need to apply to make it viscosity. And some basically we are at the end of our exposition. Next time we are going to talk about the time we are going to talk about again about polymers, and we are trying to make more sense of our discussion about injection molding, etc. So about the need for measure the viscosity and so on, and also about the fact of effect of the glass transition temperature. And we are going to concentrate also on the creep of polymers, which are just passed through. So, so with that, we need to make more sense of this their own mechanical. As always, I will put the slide on my page and as well a few minutes to be. So we are going to meet again on Monday. And meanwhile, have a nice weekend.